Bismillah ar-Rahman ar-Rahim. I will do video number 3 of Chapter 5, Biology. Well, as engineers, we use equations, we use models to find and to estimate and to predict the population growth. The three models that we'll be using in this class is unlimited, exponential growth, space limited, and resource limited, monode. Okay? Let's start with exponential or unlimited growth. And this is unrealistic. You don't expect the microorganisms to have unlimited growth. Of course, there is limitation in food. Of course, the microorganism has limitation in age, and of course, some toxic chemicals, some limitation in food, and of course, limitation of the space. And this is not realistic, but we'll start by exponential and unlimited growth, which can be explained the growth of many microorganisms. The change of X with time, X is biomass, okay, is equal the mu max, the maximum growth rate, times X. This is equivalent to, remember this equation? dx over dt is equal k. So k is equivalent to mu max. The maximum specific growth rate is the mu max. The unit for that is 1 over day, or day to the power minus 1. And this is, of course, the first order rate constant. We are still in unlimited growth, or exponential growth. In the exponential growth, we are assuming that the energy is directed to the growth and are unaffected by resource competition. This is not realistic. It should not happen all the time, okay? Of course, the growth and the resource competition should be affecting each other, but we are assuming there is direct energy is directed to growth and no effect to resource competition. So dx over dt is mu max times x. But energy reserves are also used to support cell maintenance. Remember that we talked about rotifers, we talked about cilius, about all these microorganisms. They use their energy, the energy used from the system to support cell maintenance. And of course, reproduction. And of course, we are using all of this. We are using the first order respiration or decay coefficient, Kd, to account for this maintenance and reproduction. So you have to add this to it, dx over dt minus kd times x. Kd is called the endogenous decay or the death rate. Of course, things that are being used to maintenance, and since something is being used from the energy to reproduction, you have to account for this into the equation. So we are having this equation, dx over dt is equal mu max times x, and we have this equation, dx over dt is equal minus kdx. Now we sum it together. So it will be like this, dx over dt, mu max minus kd times x. Go back to calculus. Now we have to do integration. So if you integrate this, you will get the equation like this. xt, biomass at any time t, equal biomass at time 0, originally, times e to the power maximum growth rate, mu max, minus kd, endogenous rate, times t, okay? And mu max minus kd, well, sometimes they call it mu net. So mu net is your mu max times minus kd, which is the net effect of energy applied to growth minus the energy applied to respiration, okay? And of course, x is also indicate biomass concentration that can be expressed as the one we showed in the first slide, milligram dry weight per liter or dry weight per liter. Let's look at this example and then we will see the answers. Consider the population or community in a batch reactor with an initial biomass concentration. X naught is 2 milligram dry weight per liter. The maximum specific growth rate is given. Mu max is 1.1 per day. And respiration rate coefficient is 0.1. This is Kd. and this is mu max, and this is initial biomass concentration. Determine what is the biomass concentration using milligram dry weight per liter over a time period of 10 days. After 10 days, let's put the equation. From the integration we did before, xt is equal x naught A mu max minus kd t. We have kd 0.1 per day. We have mu max 1.1. Time, it's 10 days. Okay, x naught, it's 2 milligram dry weight per liter. You could find xt. You could find x at day 10. Okay, so we have all of this, and you could see it here at time. You could just either do it like this or do at time 10. Day 1, it's 5. Initially, it was 5, right? What is initially at day 1? This is at day 0, it's 2. At day 0 is 2 milligram the dry weight per liter. At day 1 is 5, and then day 2, 15, 40, 109, 297. Day 6, 807, 2,193, 5,962, 16,206, and at day 10, 44,053 milligram dry weight per liter. Of course, you could see that the concentration will go from almost 0, 5 is not much, 15 is not much, 14, and you can see it will start increasing from 7 all the way to day 10, okay? And if you change the mu, of course, here we use what mu? We use mu max of 1.1. But if you use 0.2, 0.3, and 0.4, you can see that there is changes in the way that this graph could be. So the maximum growth rate will determine how this graph will shape. Okay, so I think you could revise this example, and this is a very important question that might come in a quiz later on. It's very simple, and this equation, you don't have to memorize it. I'll give it to you. Now, as I told you, the first model was the exponential growth rate. Now we come to logistic growth rate. I will finish this and stop at this point once I'm done from logistic growth rate, and then I will carry the last model, the monod model. This is now we have to account for the effect of carrying capacity. Of course, the exponential growth model is also called a limited growth. There is no limit. Doesn't make sense. There is upper bound or constraint on the biomass. There is no upper bound, and that does not make sense. In the exponential growth model, there has some suitable application, and we can learn from this model a lot. However, the logistic growth model provides a framework for the situation that is concerned with limits to population growth. A logistic growth model developed for a batch reactor by modifying the exponential growth model to account for carrying capacity. Now we have to account for carrying. Every model has a maximum capacity. So dx over dt, mu max minus kd, this is what we remember, times x. But now we have to account for 1 minus x over k. K is the carrying capacity in milligram dry weight per liter. That is the maximum sustainable population biomass. So this equation is for this model. Of course, for a small population size, when x is much smaller than k, then the above logistic growth model will be converted to unlimited growth. Now we're going to go back to the previous one, the first one. If x is much lower than k, okay? Which means that we are not close to the carrying capacity. We could apply the first model. Let's look at this example. Consider the population from example 5.1, the one we just solved before. X naught is 2 milligram per liter, that's X naught. Mu max is given, KD is given, but with a carrying capacity of 5,000. There's limits. Determine the population of biomass over a time period of 10 days. After 10 days, what will be the population biomass? Let's look at, provided using the same equation here. he gave you the K, the carrying capacity K. Remember the equation? This is the equation used. So you have everything. You have mu max, you have KD, you have, of course, you could integrate this equation to have this X and K and X and then find out the time. Okay, so let's look at this. Biomass. When you go from 0, of course, here account for mu max minus KD, biomass 2, 7, all the way to 5,000. That's where you are reaching the carrying capacity at day 15. At day 10, look at it, 4,124. This is for logistic growth examined. Now, if you plot the exponential growth, you can see that this is not realistic. It will keep going all the way up, assuming that there is no carrying capacity. But while you are doing the logistic growth, which little bit makes sense, that every system has maximum capability. Logistic growth will increase like the exponential growth, but there is limitation that the carrying capacity will not reach. Okay, so these are the two differences, and we will stop at this video and then we'll do the next video next. Thank you.